All right, so the other night in class, or the other day in class, depending upon which class you're in, we spoke about the second hand on the clock rotating around and used that to motivate the idea of angular velocity or angular speed. And so let's go back to that and think about this second hand here. And so we have a second hand in this position. And then if we think about 15 seconds later, the second hand has traveled a total of pi over 2 radians. And if that second hand is 3 centimeters long, then in theory, we can start to perhaps visualize that as that was occurring, right, as that tip of that second hand was rotating around here, if you were an ant, maybe riding on the tip of the second hand, you could imagine yourself moving through space, right? 1 second, 2 seconds, 3 seconds. You're moving through space over time. So it makes sense then, if there is some angular velocity, to think about the linear velocity at the tip of the object moving at some angular speed. Well, we know how long it took for the ant on this ride to go from, let's say, point A to point B, right? It traveled along this this sector circumference there of the second hand as it went from the top to the 15 seconds later. So we know it took 15 seconds, and we know the angle that it traveled, and we know the radius, so we know that this sector's arc length is going to be equal to the radius times the angle, and so that's going to be 3 centimeters, and we're going to multiply that by pi over 2 radians, and again, the radians are non-unit, and so we get 3 pi over 2 centimeters is how far the ant traveled in those 15 seconds. So if we want to think about the speed of the tip of the second hand, right? And then, of course, it's important that it's 3 centimeters long, because if the second hand was longer, the tip of it would have to move faster to cover the same angle in the same amount of time. So the speed of a tip of a second hand 3 centimeters long is going to be, and we can call that the velocity. Well, that's going to be how far it moved divided by how long it took, right? So this is going to be the distance, and this is going to be the time. Same if you went 60 miles in 1 hour, you went 60 miles per hour. And so our distance is 3 pi over 2, and that's divided by 15 seconds. And so that's going to be centimeters per second. And that's kind of an ugly number there, but we could simplify it down and come up with the decimal approximation. That's not our concern. Our goal here is just to motivate the idea that the tip of that second hand was moving, and that we can use the formula how far the tip moved divided by how long it took to discuss the linear velocity of the tip. Now, we have the formula r theta for s that we used here, so we could actually combine those together, and we get two formulas now. So the first formula that we get is that the velocity is equal to how far it moved divided by how long. The second formula, placing r theta with t, replacing s with r theta, and that gets us r times theta over t. But this here is the angular velocity that we described the other night, and so that's r omega. However, in order for you to use omega, the angular velocity, and just multiply it by the radius to get the linear velocity, that must be in radians per unit of time.